Next, we have Florian Suri-Payer from Cornell University, who will be presenting their title, Basil, Breaking Up BFT with Acid Transactions.
I'm really excited to be able to talk to you today about a system we built called Basil, where we try to rethink how to build performant but expressive BFT databases. Before I get into Basil itself, I want to start by briefly building our context by revisiting the simple but beautiful abstraction of totally ordered ledgers that lies at the core of most BFT or blockchain systems. Now, this is a really powerful abstraction because it allows us to have mutually distrustable parties that are able to replicate and share data, well, regardless of some amount of parties compromising or acting in a malicious way, they can still agree on a common view of the system state. And by totally ordering transactions, we can trivially maintain traditional ACID guarantees such as atomicity or isolation, which makes it easy for database applications to materialize key value stores on top. This is a really powerful abstraction and desirable abstraction for our applications to build around, but implementing it in a fairly scalable fashion is challenging. On the one hand, ordering is costly. There's both permissionless and permission systems. I'll be focusing on the permissioned ones. We usually need several round trips of communication between the replicas. We usually rely on a dedicated leader to act as a sequencer. And we usually have costly and quite complex recovery protocols that, not without reason, give BFT a bad rep for being overly complex. On the other hand, while executing transactions sequentially is trivially safe, that's an obvious super bottleneck. And to make matters worse, this kind of order execute pattern usually forces us to use restrictive transaction models such as stored procedures, one-shot transactions, or even UTXO models that in practice database systems don't actually use very much. So in fact, there was this interesting study in 2017 performed by CMU that showed that the majority of database systems use stored procedures less than 10% of the time. So we want to strive to do better than that. In general, it's not hard to see that all this coordination, this ordering, the sequential execution is overly heavy-handed for most real-world workloads that consist largely of commutative operations. Right, these transactions of Alice and Bob are trying to buy a race car, gelato, respectively, could have been safely executed in parallel. And that's by no means a new observation. We were hearing several talks earlier about how to use sharding and how we can use that to leverage increased parallelism in our systems. But what I want to highlight is that while we definitely agree that sharding is necessary to scale our resource horizontally, using it to achieve parallelism is more of a side effect that's dependent on our workload and the quality of our partitioning. So really, within each shard, we still retain this total order. So really, for the most part, sharding is a band-aid that allows us to recoup some of the parallelism that we've artificially removed by totally ordering. Additionally, when we have multi-shard transactions, we need to run some sort of distributed commit protocol, like two-phase commit. And now we're enforcing coordination for consistency twice, both to replicate within shards and across shards to maintain safety. We also can't shard arbitrarily because increasing the amount of shards for multi-shard transactions increases the communication cost for coordination linearly, which is especially costly for signatures in BFT. Now, what we propose instead in Basil is to take a page from our crash failure-based counterparts, and instead of implementing this total order, strive to implement executions that are equivalent to a total order or serializable. So take, for example, the executions down left. What serializability states is that Alice, Bob, and Charlie's transactions can safely execute in parallel and in a non-atomic fashion because their operation outcomes are equivalent to the sequential execution of first Alice, then Bob, then Charlie. So in Basil, we take this idea and we build a BFT transactional key value store that offers interactive and serializable ACID transactions to scale this abstraction of a totally ordered fault-tolerant log. The way we realize this is by building Basil around the core ethos of what we call independent operability, that roughly states that all operations that can be independent should also be executed independently. So in Basil, what we do is we adopt a client-driven approach in which each client drives its own transaction processing and is responsible for its own progress. And as part of that design, we try to strike a balance between optimism that allows for aggressive parallelism, but still have robustness to failures. Right? It's not hard to imagine that by empowering also Byzantine clients and letting them be optimistic, that's a slippery slope, and doing so safely and robustly is the main challenge in Basil. At a high level, Basil is made of three core components. First, a concurrency control mechanism that allows for optimistic parallelism but ensures serializability. Second, a commit protocol that is integrated with the concurrency control protocol to avoid redundant coordination and efficiently ensure consistency both within replicas and across shards. And lastly, a fallback protocol that allows clients to retain independent reliability and liveness in the face of Byzantine client failures. Now, it's actually not immediately obvious how to even quantify serializability in the presence of Byzantine clients. So in the paper, we also spent some time quantifying that. In the next slides, I'll briefly go over parts of these protocols. But if you're curious, I do encourage you to read the whole paper if you want to know more about the details. So let me start by very quickly outlining how execution works in Basil. So clients use this interactive transaction model and executes the transaction in parallel with other clients. Reads are sent to local replicas, and importantly, since those could be Byzantine, they need to make sure that A, of course, these are valid values, which you can do by just adding signatures, but also two, that they're not tricked into reading arbitrarily stale values. Instead, writes are buffered locally in order to delay the visibility until commit time. And that's an important property for recovery that I'll touch upon in a little bit. But the intuition here is that we don't want Byzantine clients to be able to leave incomplete transactions lying around arbitrarily. Now, of course, any such speculative execution performed by clients in parallel might not be serializable or Byzantine serializable at all, so we need to validate them before being able to commit. And the way we do that is by having clients submit their completed transactions to all replicas and all involved shards, who then vote on the local safety of this execution by running an efficient multi-version concurrency control check. Clients just collect these votes from a shard, and if sufficiently many deem this transaction locally serializable, then we can conclude that it's safe to commit on any given shard. Right? When we have multi-shard transactions, clients simply aggregate the quorum of votes to form a two-phase commit decision. And in most cases, when there's no contention or failures, this decision is immediately durable, and clients are able to directly commit in a single round trip and return to their application. Now, of course, that might not always be the case. When we have contention and concurrent transactions, they may conflict, which causes some transactions to either receive fewer commit votes, in this case Bob, or to be forced to retry their transaction and abort. Now, in that case, we do need an additional round trip to make this two-phase commit decision durable. But what is really cool in Basil is that we can do this on only a single shard, no matter how many shards are involved in execution in total. Now, another thing that is really cool, but I don't have time to go into detail, but I do want you to take away, is that Basil's commit protocol, this client-driven design, is designed in a way that allows neither clients nor groups of Byzantine replicas to single-handedly dictate the results or the transaction outcome, right? Whether it should commit or abort. In our paper, we formalize this as a general BFT system property we call Byzantine independence. This is a really strong property that most traditional state machine replication or BFT protocols don't meet, because a leader that they rely on as a sequencer has undue control over the ordering and can inject transactions for front-running. This ordering concern is really important in many financial applications, and actually conveniently saw that Mahimna is going to talk about this later, so I'll leave it to him to convince you of the importance of this. The takeaway here should be instead that Basil, with its client-driven design, sidesteps all of these concerns of ordering and fairness entirely. Now, what I did swipe under the rug in the previous 4 slides, but I kind of alluded to previously, is the fact that by empowering clients, I'm in particular also empowering Byzantine clients. Now, if their transactions are commutative, then that has no impact on other clients. But if they do conflict, then misbehaving clients can block contending transactions to stall indefinitely or even force them to abort and have to retry. Now, the way we address this in Basil is by allowing any client to drive the commit protocol for any transaction. Now, that's perfectly safe because I already told you we delay the transaction visibility until the commit time. So we're not accidentally stealing away incompleted transactions. And B, like we just talked about, clients are not able to decide the outcome of a transaction, and hence it doesn't really matter which client coordinates the commit. Now, this recovery protocol has some nice properties. It requires usually only a single round trip. It also only involves a single shard and does so with linear communication. Now, like with most BFT protocols, the details can get fairly involved, but what I find especially cool is the fact that clients are A, in charge of their own liveness, but also B, recovery only affects contending transactions. And that's unlike existing view change protocols that have to hold all transaction processing when the leader is under duress. Of course, with this client-driven design, there's several other challenges, such as dealing with equivocation or live lock with multiple clients, which I won't talk about now, but reading about those in the paper is one of the many pleasures you'll have in reading the full paper. Yeah, at this point, I want to cut short this short overview, this ever so brief overview I gave you of Basil, give you a quick recap and resume. So we built Basil, which is a replicated and sharded BFT database. It implements interactive transactions that offers a flexible application interface for developers. And it meets both these properties of Byzantine serializability and Byzantine independence that I kind of alluded to, but we define in more detail in the paper. And on the performance side of things, it allows transactions to execute in parallel rather than sequentially. It allows them to commit across shards in just a single round trip in most cases, and does so with linear communication complexity and without incurring the potential scalability or fairness bottleneck of a leader. And lastly, like what we were just talking about, it allows for independent failure handling for commutative transactions. All right, so before we end, I want to briefly talk about how this design translates to practice. So what we did is we implemented a prototype and we evaluated it by implementing also 3 common OLTP workloads, TPCC, small bank, and RedTwist, that all use interactive transactions but experience varying level of contention between their transactions. So on the left, we compared Basil to Taper, which is a recent crash failure state-of-the-art database that also uses similar client-driven design and also integrates the distributed commit and replication layer. And here, Basil's main overhead stem from the fact that it requires signatures and larger quorums for BFT, but nonetheless, it offers quite competitive performance given the increased security and resilience to BFT. Now on the right, I'm showing you a comparison of Basil against 2 BFT baselines that also both are built to offer interactive transactions and concurrent execution, but unlike Basil, follow this kind of standard modular approach that layers 2-phase commit and concurrency control atop black box consensus protocols, in this case, hot stuff and PBFT, or its implementation BFT Smart. And here we can see that Basil significantly outperforms both, mainly in this case because it avoids this redundant coordination during distributed commit, which reduces latency down to a single round trip that in turn translates to throughput on contention bottleneck workloads. Now, it's obviously great that Basil achieves this performance during gracious execution, but that was partially achieved on the back of the premise of empowering Byzantine clients as well. So to validate how robust Basil remains when clients do misbehave, we also evaluated the impact that Byzantine clients specifically have on the transaction possibilities of correct clients, right? Because that's in line with this ethos of independent operability of each client driving their own transaction. So clients may fail in many ways. They may install their transactions during commit, which causes contending transactions to block. But Basil's recovery protocol allows them to very quickly complete some transactions, and in fact, without in most cases to having to abort at all, because our concurrency control mechanism also allows clients to form redependencies on prepared but uncommitted transactions. So these failures are just turned into blocking, and after some sort of delay, the transactions finish anyways. So I was showing here the impact is fairly overseeable. Instead, the worst failure that clients may do, which is, however, also detectable, is that they may try to equivocate, they may try to replicate inconsistent results or proposals during the logging phase of the distributed commit. And that incurs significantly higher performance penalty, you can see in the red box, because recovery is more involved. But fortunately, like I told you earlier, Basil doesn't actually allow clients to themselves choose what proposals or what values to propose. So this was an artificial simulation where we allowed them to always equivocate, but in practice, you can see that in the green box, we show that the ability to equivocate is exceedingly rare in practice, and that makes the strategy impractical or infeasible to pursue. So overall, we can show that despite more than 30% of transactions being faulty, Basil is not just live, but robust. It has robust performance because failures only affect conflicting transactions, and when they do, they can be recovered swiftly. All right, at this point, I want to end by concluding that we showed with Basil that using this client-driven design, it is possible to still build this abstraction of a BFT totally ordered log, but do so in both a highly concurrent and yet highly resilient way. And I know we had very little time to talk about the interesting technical bits, so feel free to ask me in the Q&A or send me an email. And in our paper, which I've linked here, you can find detailed discussions of the protocols that compose Basils and several other micro benchmarks to help understand the performance profile. Thank you.